Welcome everyone. My name is Charlie Day. I am the Director of Training and Professional Development at the Texas Advanced Computing Center, also the Design Safe Training Lead. I'm here today with one of the co-PIs on Design Safe, Scott Brandenburg, and Trevor Carey. And we'll get started here in just a bit. But, oops, wrong window. Of course, welcome. We have some interesting news going on at Design Safe, so feel free to hit the Design Safe portal site and go through the news items for the day. I think all of you have been mailed an email with a link to a survey. We ask that you, after this webinar is over, that you please fill that survey out for us. We'd love to hear your feedback, and we really appreciate it. If you did not get that particular email, here is a link and a QR code that you can just scan with your phone, and it'll take you to that survey. Like I said, we really appreciate it after this presentation's completed. If you can take the survey for us, that'd be great. All right, so moving into today's topic is the experimental data workflow for real-time decision-making using Python and Jupyter notebooks. As you know, Python has become the go-to language for data analytics and data analysis. And of course, Design Safe has featured Jupyter notebooks since its oncoming. So with that, let me tell you a little bit about this webinar. This is going to focus on the experimental data workflow that is becomes center to Design Safe and real-time decision-making during experiments. And we're going to be using an example from the Center of Geotechnical Modeling. So they're going to leverage Python and Jupyter notebooks for this particular webinar, and they're going to look at some data collected during experimental testing that we can process and synthesize and make informed decisions. Trevor Carey is going to be our presenter today. He is a postdoc scholar at the Department of Civil and Environmental Engineering at the University of California on their Davis campus. His primary research interests are physical and numerical modeling of liquefaction hazards. And he's performed several liquefaction centrifuge experiments through the Center of Geotechnical Modeling during his PhD and his postdoc. So with that, I'm going to hand this off to Trevor. Thank you so much for joining us today, and I'm looking very much forward to your talk. Thank you. And with that, I'm going to stop my share and hand it over to you.
All right. Just going to share the second screen there. Hopefully everyone can see it now.
Yeah, and everyone, if you have any questions for Trevor, please use the Q&A button on the bottom, and we'll be monitoring that.
All right. I'll go back a little bit here. All right. Thank you, Charlie. I thank you for everyone for taking time out of your schedule to be here today. Good morning and good afternoon, depending on where you're located. Before I start, I'd like to thank the Design Safe team, Charlie, Scott Brandenburg, and Natalie for giving me the opportunity to come speak with you today. I'm excited to share some of this work that we've done and kind of understanding of experimental data workflow and real-time experiments. The title of my talk is Experimental Data Workflow for Real-Time Decision-Making Using Python and Jupyter Notebooks. Kind of an overview of the talk today. I'm kind of an introduction of time-sensitive experiments and what that means for rapid decision-making. Centrifuge testing, kind of give you an overview of where the need was for time-sensitive decision-making, and kind of give you the workflow of a centrifuge experiment, and then the required decisions just during centrifuge testing. We'll move into some data processing routines, and that's the developing of these routines, when to develop these processing routines in the design of an experiment, and the benefits of those routines. And then I'll kind of integrate those routines in some kind of rapid decision-making framework. And this is for making decisions during experiments, integrating data processing decision. And I'll kind of talk about that using an example of a liquefaction experiment. I'll end with kind of decision tree implementation using Python and Jupyter notebooks, an overview of Python, and then some of the data processing routines and evaluating decision trees. Given kind of the shortness of a seminar today, I'm not going to go too much into kind of the coding that would be required in Python or Jupyter Notebook, like the specific aspects of the nuances of the code. And that's just because I want to keep this kind of for a broad-based audience. As I'm going through today, try to think of this decision-making framework not in the context of centrifuge testing. I use that as kind of my vehicle for examples because that's what I know the most. Think about this for the experimental work you're doing or the numerical simulations. This framework and this idea isn't just limited to centrifuge testing or large-scale experiments. All right. When we start to think about time-sensitive experiments and rapid decision makings, what comes to my mind is all the NARI facility sites. And these all have some kind of time-sensitive component of the experiment. And that's partly because we don't have forever, we can do all these tests. We can't be on these facilities and occupy these facilities for months on end or years on end to get the exact data we would want for some kind of analysis. There's also kind of environmental changes. So if we think about concrete 28-day age strength at day 6, it's going to be different than day 28, than year 28. Also at the Rapid Center, that a post-disaster reconnaissance will look different from day 6, day 60, or year 60. So understanding each one of these components is a different aspect of time sensitivity. How I kind of define time-sensitive experiments or requiring rapid decision-making are operational. So this would be the NARI facilities. We are resource limited. We can't be on the centrifuge arm for months or years on end. And that's because there's other teams behind us wanting to get on the arm. We don't have infinite funds or infinite time as well. There's also environmental changes, and this is the concrete day strength or the post-disaster recovery is understanding that a study system will change with time, and we need to be able to understand that that change will change what we're actually looking at. Rapid decisions are required for phased experiments. Most of the experiments that we do at these large NARI facilities are phased experiments, and I'll get into this in a few slides about centrifuge testing, and it's because there's a lot of effort that goes into developing these experiments and implementing them. And so we try to get the most out of them as possible. That's not always the case. Sometimes we're one and done on some of these experiments, but oftentimes there's a phased approach and we're looking at specific aspects. These rapid decisions will impact project outcomes. They have a direct correlation to what we're going to get out and what we're going to record in these experiments, but they also need to be made with the experimental time frame. We can't make these experiments over weeks or months sometimes. Sometimes in the case of centrifuge testing, we're spinning, and this could be something that we need to think about within the next 5 to 10 minutes of testing. Now I'm going to kind of give you a quick overview of centrifuge testing, and this is what kind of drove the development of this experimental workflow and rapid decision making on my sense, is kind of a recognizing that there's a lot of work that goes in these experiments, and we should be really trying to best understand them we can. That way we can make better informed decisions. So centrifuge experiments typically start out with a design and review. This design is understanding what containers you want, what soils you want, what sensors, what the layout of this is. And there's a lot of iteration on this design after meeting with the centrifuge staff that have worked on these models for years. And then this goes into an iterative approach. There also might be some work done at a home research institution to try to characterize the materials that we're interested in. This then feeds into kind of some on-site work. Once your design has been finalized or near finalized, you come onto on-site, and that's when you start to develop your pluviation procedures, calibrate sensors that are kind of standard operating sensors at the center, or develop new sensors that you need in your model. Shown in these two photos, this would be instrumenting some structures with strain gauges, developing pluviation procedures. That then moves into the model building, and this is when you start to see your designs come to life. This is you're taking what you did on paper and actually building it into the model. So kind of shown here going from clockwise left to right on the top, we have the sensor placement, we have a pluviation, and then on the bottom figure there, we kind of have a placement of a treated soil block in a model. This then kind of funnels down to mounting this on the centrifuge arm. I want to say that these are kind of some really broad-based activities on the centrifuge. Doesn't get really into the details, but we mount the centrifuge on the mount on the centrifuge the model, and you hook up all your sensors and you hook up all your data acquisition systems, and then finally you get to testing. And hopefully soon we can all get back together and have testing situations like this. We're going to have a bunch of people in the room watching the results. When we think about kind of this process of centrifuge testing and what that means, we actually, as we go down from design to testing, it actually gets quicker. Time on task gets quicker. So design and review can take months. As we get to on-site model building, that goes from weeks to days to hours to minutes. And for those of you who have not done centrifuge testing before, when we scale time in a centrifuge, so when you actually subject a centrifuge with a ground motion, it'll be sometimes less than a second or less than a half a second. So I don't actually have that listed here, but we go from months to seconds. And it's always a challenge when you spend months thinking about these problems and these experiments to be summarized in less than a half a second. So kind of the key attributes to this is the progressive stages of testing are quicker, but the cumulative time to get to those stages is high. And we can't reset or restart during later stages. And that's because we may not have the funds to do so, or there might be other people behind us that need the equipment. And during the testing stage, rapid decisions are required for phase testing. And kind of my thesis for kind of explaining what the centrifuge workflow is and the background behind that is the effort to get testing stage, the effort to get to the testing stage drives the need for decisions made during that stage to be well informed. We can't just reset the model or redo the analysis. So dynamic centrifuge experiments, so these would be liquefaction experiments or anything that's shaking a model, which is typically the bread and butter of the centrifuge, routinely have a sequence of ground motions. And that's again because we don't want to do a one and done on these experiments. We want to subject them to a series of ground motions and see the evolution of the model. The range of ground motion intensities and how strong we're going to shape the model is often not finalized prior to testing. And that's because we don't know how the model is going to respond during shaking. If we knew that, we probably wouldn't need to be able to develop these models. So kind of showing here on the right-hand side is a typical shake sequence of 4 shakes. And you can see here the PGA, which is the peak ground acceleration, the peak acceleration we're putting in the model is increasing with these shakes. And Errors intensity is just a measure of energy of those shakes. As you're looking at this, you can also tell that we try to increase the energy or the PGA or the amplitude as we increase shakes. And that's because we don't want to shake it with the hardest motion we can first, because the system will no longer be the initial system that we had hoped to be at the start. The knowledge of the model performance from prior shakes is often used to evaluate or select the future intensity of the ground motion. So all the shakes that you see in this figure, shake 1 or shake 2 was typically, or shake 1 was informed upon shake 0, and shake 2 was informed upon shake 1. So using that information and building on it to create a better decision and kind of a more informed decision of the model response during shaking. And the reason we do this is because centrifuge experiments are highly nonlinear. Once you shake the model, there's no coming back from that. You know, even a series of small shakes will change the state of the soil or potentially the geometry of the system. So you can't reset or redo. The models are, once you're shaking it, once you've liquefied it, that's it. There's no more. And to kind of give you an example of that, here's a video from a recent test of, these were some foundation structures on some MICP improved soil. And you can see the shaking there. And the structures, they settle into the soil below. And here's a photo of what that looked like afterwards. And so you can imagine if we didn't have the correct shaking or the correct intensity of shaking, we might have immediately put those or buried those structures and made them settle early on in the process. So having a good ability to recognize that, yes, we don't want to have this happen immediately, but how do we get to kind of a staged approach and causing these to kind of settle over time among different phases. It is the responsibility of the researcher at the centrifuge typically to extract the knowledge from experimental data. And what I mean by extracting knowledge is that's the data that has been collected with the data acquisition system on the centrifuge. I'll kind of use that phrase several times today. It is the facility and staff of the centrifuge have developed processes and routines that are kind of common amongst all centrifuge experiments, but it's up to the researcher to kind of know how to apply that in their model. What specific array of sensors, what things are important to show that. But often the data processing routines to extract knowledge are not fully developed prior to testing. These aren't typically developed by the researcher until afterwards. And that's because there's a prioritized completion experiment over the increase in your knowledge or the knowledge we're trying to extract from the experiment. These are often seen as kind of separate tasks. You have the experiment, you have the processing, and then you have the write-up of the data. But actually everything's together and kind of as one unit. This is a missed opportunity to for fully informed rapid decisions. If you're only looking at a specific aspect of the response of the system, you're not fully forming your thoughts and understanding of that. These ideas kind of then made me start to think about the data processing routines of what things do we need and why do we need data processing routines in centrifuge testing. A single experiment has significant amount of data, and we collect that data because it has some value or some interest to us, but we don't need to know every single response parameter, every single response of the sensors or in an experiment to understand the experiment. And we typically, only a few main behaviors of an experiment are of interest. And these would be the usual suspects in any kind of performance-based design, such as a peak drift, a peak base shear, a deformation of a slope, or some kind of strain criterion. So those are the typical suspects of what we really actually care about in the experiment. And a phrase that I'll use kind of throughout this presentation is those aspects are experimental response parameters. And those are what we care. Those are what's driving our decision-making process and understanding of what's going to happen and what we're trying to target with the test as a whole. When developing data processing routines, the experimental response parameters of greatest interest should be prioritized. Again, if we have 200 sensors, we may not need to plot up 200 sensors to prioritize that behavior. When you have so much information, it does get really hard to make an informed decision. You need to kind of focus in and narrow that scope into what specific aspects we actually care about. Before the development of routines, current hardware or software limitations may inhibit rapid data processing should be known. An example of this I can think of off my top of my head would be high-speed video processing. High-speed videos are used kind of more frequently in the last 10 to 15 years to track displacements of a system, but it still takes maybe hours or if not sometimes days, depending on the number of images, to convert those to a displacement time history. Those are still valuable tools, but they may not be accessible to you during rapid decision making. So that should be something considered ahead of time. When to develop these data processing routines is kind of a question that I struggled with in recent centrifuge experiences that I had. And I thought about these things and when I should do this. And I've come to the conclusion that the development of processing routines should be done in kind of parallel with the experiment design. This promotes a review of the routines themselves and of the experiment. And you can kind of answer the kind of a mirrored question here of, do the processing routines provide adequate information about the experimental response parameters to make decisions? Do you have the right routines to understand the experiment? And then kind of on the flip of that, the reverse of it, does the current experiment design efficiently produce the desired output data? An example of this is shown here as a centrifuge test for LEAP, which is it was an international collaboration to validate numerical models using centrifuge experiments. And one of the important parameters from these experiments was stress strain data. And stress strain data in centrifuge experiments typically comes from an inverse analysis procedure using accelerometers, which are shown here with these pins. And so by walking through the process to do inverse analysis and stress strain data, you'll start to understand and start to see, if I have my sensors placed too far apart, I may not get the resolution of data that I need. The pore pressure transducers, I want those between the accelerometers to tell me the pore pressure response during that stress strain behavior. And kind of saying that data routines kind of this highlights that data routines should be fleshed out as much as possible when you're doing this. It's easy to say, we're going to do stress strain response on this array, but if you actually walk through that process, you could actually see, oh shoot, again, the sensors are too far apart, should bring them back in together. So the more time you spend on those routines, the better kind of the payout will be in understanding if your design is most effective. And this is a challenge sometimes because you're having to develop routines for data that you haven't collected yet. And that's where I'm going to say, I think this is a great resource for Design Safe that Design Safe has, where you can go to the databases and you can look at the published data sets that are available. Oftentimes people include process data, raw data, or some kind of in between, and you can use that to validate of processing routines that you're developing. I've done this, and I find it incredibly useful and helpful to understand and kind of see how others have done it, and kind of replicate that and make my own routines and kind of advance those and move those forward. Some of the benefits of the data processing routines, I've kind of already touched on that, but experiment design modifications made following review of data processing routines may improve the robustness of the collected data. Again, you're getting a better bang for your buck. Real-time understanding of experimental evolution to make better informed decisions. You know the state of the model moving between events, and so you can make a better state of the model when you're doing those subsequent shakings or whatever have you in the experimental testing or numerical simulations that you're doing. This saves time between experiment phases. This is kind of an underrated aspect, but if you create a script or some kind of processing routine that generates the same data every single time, you can run your scripts, show that data, and look at that and evaluate it. If you don't do that, you have to maybe use Excel or some other kind of plotting program to look at the experimental data. And that can obviously, if it's not scripted, it's going to take longer to do so. And you may not be looking at the same things every time. You may not be looking at apples to apples. You might be trying to compare apples to oranges at some point. And then the important part, and I'll touch on this later, is it reduces the likelihood that specific mechanisms are missed. And centrifuge testing and probably much experimental testing, we're always trying to target a mechanism or a behavior with these experiments. And so you can miss that if you overdo it. Again, if you think back to the shaking sequence of a centrifuge, we can do really small shakes easily. We can do really big shakes. That's not that challenging. It's the middle of those bookends that is the challenging part. And that's the part we really need to focus in on, because a small change in the ground motion in that middle can really change the response of the model. And then finally, and this is something that I find interesting too, is the information from data processing routine is often included in final reports or publications. This is not a sunk cost. Spending time in developing these routines and these procedures is something you're probably going to use later, because the interest for publications is interest in testing. If it's not something that you're going to include, or at least a component of it in a publication, is that the right thing that you should be looking at for the centrifuge or the experimental response parameters? So data processing gives us a state of the model, but it doesn't necessarily tell us what we should do next or give us rapid decision tools. So the knowledge gain from data processing, the responses that you have just seen, is used to make future decisions about future phases of testing. Data processing itself and the results and the knowledge gain doesn't actually do that for us. We have to then make the next step and say, okay, we have this response. We want to target this response next. This is what we should do differently, or this is how we'll change the next phases of testing. And this idea or procedure is not necessarily limited to just experimental testing and experimental work we're doing. This is often done in numerical simulation or laboratory testing, where we say, okay, well, this is the response we got from this soil sample at this stress and this cyclic loading. Let's change it to inform what we're going to do next. I will say, and I kind of mentioned this with the kind of overview of centrifuge testing as a whole, the significance of a decision increases with the complexity, cost, and time of the experiment. While these are the same decisions, if you mess up a laboratory element simulation or element test, you may be out a day and a half. A numerical simulation, you can just hit reset. As you saw with that picture and that video of the foundation settling into the model, You can't redo that. Once that's happened, it's done. And that kind of makes dynamic centrifuge testing a real, it's kind of a function of decision making, or a process of decision making. So to effectively integrate the knowledge gained from data processing routines requires decision analysis tools. And decision trees, I find them as an effective tool for rapid decision making. So taking the knowledge we've gained from experiments from the data workflow routines, and then using that to now make a decision. This is a common decision that I have to make every morning as I go into work is, do I need a jacket? And you probably make similar decision trees like this implicitly in your everyday environment. So do I need a jacket today? Well, is it raining outside? Yes, well then I need a jacket. Is it cold? No, so I don't need a jacket. The researcher or the person deciding kind of evaluates each one of these conditions, and they are the ones that say whether it's cold outside or whether it's raining. You go down these decision trees or these branches until the goal is reached. And the goal in this case is really, do you need a jacket or you don't need a jacket? The real benefits of these decision trees is this gives you a path of testing priorities. So you kind of know what comes first in this process. Is it cold outside? Maybe not as important as it's raining outside. So it kind of gives you a hierarchy of what things you should be looking at, because there are events or tasks that are results of other events or tasks. This also gives you kind of a discussion of when a test has been completed. What criterion are you going to use to say this test is done, we don't need to keep doing testing, or should be stopped? So that also helps to kind of define that with a decision tree. I'm now going to walk through an example of a decision tree for a liquefaction experiment. So this is an experiment that I recently ran at the Center for Geotechnical Modeling. Just kind of the goal for this experiment was to characterize the dynamic response and embankment during liquefaction. For those of you who have not done centrifuge testing, this would be kind of the model scale proportions of this model. So this is what for the prototype scale dimensions. So this is what we're trying to achieve when we spin the centrifuge. This experiment just consists of a flat bench, a 10-degree slope, and another flat bench with some liquefiable sands underneath it. The experimental response parameter that I was interested in, and the whole reason to develop this experiment was, I guess, again, the liquefaction triggering of the slope itself. The seismic sequence, again, this is phase testing, so looking at several different earthquake motions, was an elastic shake, a shake that just triggered liquefaction in the model. Cyclic mobility, for those who are not familiar with that, that is additional cycles of acceleration or loading following the triggering of liquefaction, and large deformation. So wanting to take that slope and make it completely flat like a pancake. For those of you that aren't really versed in this type of work, you may see those 4 shaking events and say, yeah, they're all about the same. And they're not. Actually, each one of those shaking events or those targets was to look for a specific mechanism in the soil response and the system slope response during strong shaking. So it would have been easy, again, to get the elastic shake and the large deformation. You can just command a small shake and a very large shake. It's that kind of in-between gray zone of triggering liquefaction, cyclic mobility is where the informed decision-making and kind of the data processing routines are most valuable for trying to target that specific behavior. So now I'm going to kind of walk through the development of a decision tree for this experiment, kind of the decision tree that we use to evaluate those different phases of testing and moving up to the next phases of testing. So for this case, we just said, did liquefaction occur in the model? And that criterion that we're going to use is just when the excess pore water pressure ratio of RU is equal to 1. This is just simply the gravity forces of the soil is equal to the water pressure pushing up, kind of a common definition of liquefaction. Going down on the right-hand side of this path, we say, well, no. Did liquefaction occur? No. What would we do then? Did RU exceed 75%? So did we get 75% of liquefaction? Yes. will increase the shaking intensity by about 20%. If we did not get that, maybe we increase the shaking intensity by about 40% and consider adding more cycles of loading. So getting stronger and stronger events into the model. On the left-hand side, we go down to, yes, we did trigger liquefaction. Where accelerations damped out at shallow depths, this is kind of a common tool that is used to evaluate the severity of liquefaction. So looking at, do we see the acceleration of these top surfaces starting to damp out? No. Increase the shaking intensity by about 20% then? Yes. We drop down into another level of, did the dynamic strains exceed 10%? Think of this as, did the slope completely flatten? Yes, the test should be complete. And no, maybe increase shaking intensity by 10%. So this decision tree was evaluated for each and every single shake that we did on this model. Now, if you're looking at this, you may say, well, do you always need this entire decision tree? No. As we went to those higher and stronger and more intense shakes, we didn't go to the right side anymore. We just primarily fell into the left-hand side and eventually just completely stayed to the left. So you may not use the decision tree for the entire duration of an experiment or a test, but you still need it for those early phases. So now I'm going to kind of walk through a decision tree implementation using Python and Jupyter notebooks. This is going to be kind of a higher level talk and thinking about this as kind of a pseudocode rather than implementation of specific aspects of code. And I largely did this just to make sure that we're targeting, a lot of this will be specific to the research site that you're at or the university or the system you're using. So it doesn't make a lot of sense to tell you, well, this is how we process binary data at this geotechnical modeling facility. I expect you to have the same process at your home institution. So just kind of a quick overview and thought of Python. Charlie has kind of already mentioned some of these topics. Python has many documented advantages over proprietary software. It's free, which is the big thing for me. It's constantly updated, and it's a program language or a scripting language you can use for multiple different operating systems. Design Safe has archived Python webinars and training. I think Charlie mentioned he's going to put a link for that. Those are great. I've used those before for some of the work that I've done. They're really helpful to give you an idea of what you can do for some specific data processing. You can run these Python and Jupyter notebooks on Design Safe. They have that functionality, so you can completely work from the cloud. If you're running locally, there's several distributions of Python available. And these distributions have made the barrier to entry and get into using Python a lot easier to overcome. I think this is a really good change in the last 5 to 10 years. And then finally, this is a question I get a lot. I've gotten this a lot recently, and that is Python's a language. So Python's a scripting language that you're doing. Jupyter notebooks are tools within that kind of use that language. Thinking about Jupyter notebooks for this kind of data decision-making work is they're a document that contains both markdown and data, which is really helpful when you're doing a decision tree. So you can actually plot up your decision tree, and each one of those modules, you can make that each one of those boxes. They're interactive, they're easy to change inputs and outputs, and they're great for learning. Some of the kind of the notable drawbacks that I've run into, this is kind of, that might be specific to me, but you might find the same things, is the documents can get long with a lot of code, and Jupyter notebooks may not be suited for large data sets or complex analysis. You're trying to push a lot of data and maybe just go back to the scripting. If we go back to the kind of the decision tree that I made for that experiment, each one of these boxes that you see here represents an analysis and a data processing routine. And so if we take each one of those boxes out, we can develop a Jupyter notebook or a scripting routine to synthesize the data required to evaluate each one of these conditions. So I'm going to give you kind of a quick pseudocode of what that would look like at the Center for Geotechnical Modeling. We first get input data from the DAC. This is the data that we've recorded from the Geotechnical Centrifuge. This is the output data that the LabVIEW program gets us. We do some initial sensor processing. This is zeroing transducers, converting everything to the right scale. And then we have the outputs. And these outputs map directly to the branches of the decision tree. So the pore pressure response. So we have the output of the pore pressure figures. We have the output of the acceleration response. And we have the output of the dynamic strains, or how much the model moves. Kind of the key attributes of this is the standard set of outputs are generated for each ground motion. For my purposes and kind of this example, I'm only looking at the figures or some kind of response. You may have some kind of index parameter or index number, maybe just a single value that you're looking at. It just depends on what parameters in the decision tree that you have and what you're concerned about. Only data required for rapid decision-making process is processed, and that's because, again, we want to make sure we can narrow the scope and we can see what's important in this experiment, not look at everything. Everything is important, and there is a time and a place to understand all the data that is collected in the experiment, but that may not be, and that probably is not, during some rapid decision-making process. And then finally, an automated process to avoid user inputs. And the reason I think I advocate for an automated process, and that makes sure you're doing, that ensures that you're doing the same thing over and over again, and you're following the same routines. So kind of a cartoon of what this would look like on the centrifuge. So we have a phase, or we have an event where we shake a model with an earthquake motion, which I showed here on the left. That data is then collected with the DAC. I use that data, then I transfer that data to Python or Jupyter notebooks. I then use my data processing routines to generate the pore pressure response, the acceleration response, and the stress strain behaviors from that. These outputs then are directly used to evaluate the decision tree. So with this data, we can then go to the decision tree and make our decisions. Again, the data processing routines and the results that we get from the data processing doesn't actually give us our decision. It gives us the tools we can use to make the decision, but it doesn't constitute the decision. So I'm going to walk you through one of the branches of this. And again, we evaluated the decision tree for each one of the shaking events that we considered. So again, at the top of the tree was, did liquefaction occur in the model? And so shown here these are some pore pressure responses for these pore pressures at the very top of the bench here, and then very in the middle of the slope. And then these dashed lines here represent the RU of 1. So for our cases, did liquefaction occur in the model? And you can see, for the exception of this very top left model, most of these sensors realized or reached an RU of 1. So that the model did liquefy, or did not liquefy, excuse me. So we're going to go down the right-hand path of the decision tree, which is no, it did not liquefy. And then we kind of come to this next phase of, did the RU of this model exceed 75%? Did we exceed some kind of 75% threshold for liquefaction? And yes, we did. I don't have it plotted up here, but you can see kind of here, typically, we're all about just about right under an RU of 1. So we increase the shaking intensity by 20%. And that's how we then proceed to the next phase of testing. Again, for each event, this decision tree was evaluated to understand how did the response to the model, and that way we could use that to predict moving forward. I will say, and you can probably see this in this figure, there is still engineering judgment required to understand whether these conditions are met. By implementing a decision tree, we're not eliminating completely the judgment that we have to bring to the table and to assess the response of experiments. But it gives us the tools to kind of to best evaluate or best determine that judgment and kind of justify it moving forward. So decision trees don't completely absolve us of our responsibilities and understanding of things, but it does help and aid in that decision. All right, I got some concluding thoughts on this work, and then looks like I have a couple more minutes for some questions here. Kind of the closure on this is rapid decision making is a critical aspect of phase time-sensitive experiments. Oftentimes, most of the large experiments that we're doing have some kind of phase component. If you don't, you may not need rapid decision-making and data processing routines. If data processing routines are established during experimental design, they can be used to evaluate if the current design will produce the desired data. This is a really valuable tool in saying, are you getting out what you want? Are you going to get the response you need? During testing, processing routines help track the evolution of experiment. This reduces the likelihood that specific mechanisms are missed and can save time in between experiment phases. Time to develop the routines is not a sunk cost. You're often going to use these materials. You're often going to use these materials that you develop in your publications. Decision trees are a valuable tool for making rapid decisions using the knowledge gained from the data processing techniques. This creates a logic path of priorities and helps limit the scope. The implementation of decision trees and data processing routines is well suited for Python and Jupyter notebooks. You can create kind of, if you think of that tree, you can make each one of your modules part of that tree. And then data processing tools and decision trees can be used in applications beyond centrifuge testing. Kind of thinking about this as a whole, you can use the procedures and what we've talked about today for any of the experiment applications you're doing, or those numerical applications as well. I'd like to thank you for coming to the talk today. I'm happy to stick around and ask some more questions. A little more time than I expected here. If you think tonight, after you get home and go to bed tonight, you wake up at 12 a.m. and you have a question, feel free to email me. We can chat about it some more. I'm happy to chat about this as much as you would like. And showing here is kind of a photo from the centrifuge experiment we did this summer. We're still operating the Center for Geotechnical Modeling, doing experiments. Just things look a little different these days. We have to keep our distance and all have masks on, but we're going to get back to normal operations soon. Kind of at this point, I'm going to hand it back over to Charlie, and thank you.
Hey, Trevor, there are a couple questions.
Yep.
Would you be able to show any example code that you've done, or maybe share that with us at a later date?
I can share code with you at a later date. Yeah, I was trying to kind of limit the code that I was showing because it's kind of specific to experiments, but I'm happy to share code with members of the community at a later time.
Okay, so just to let the community know that those tidbits of code will be shared off the DesignSafe website under the Learning Training Center and be put in community data.
So Trevor, I'll relay a few comments here from the Q&A, also a few questions. Can you show an example within DesignSafe? So I had a similar question too. Are your Jupyter notebooks running locally on your own computer during these experiments, or are you putting data in DesignSafe and then running the Jupyter notebook also in DesignSafe?
So for these experiments, I'm typically running them locally on my computer, and that's just partly because the data, how we have the data being processed off the Center for Geotechnical Modeling. I typically pull that to my computer first because we can't upload that directly to DesignSafe, and I just run those locally on my computer. It's kind of right at the edge of cloud computing being really beneficial. I think the cloud computing can really speed up some of the analysis that I'm doing, because it does take about 10, 15 minutes to run some of these scripts, but I think I'm just kind of at that tipping point where I haven't thought about doing it yet on DesignSafe.
Okay. I think some of the experimental facilities do get their data more immediately into DesignSafe.
Yep.
So as a PI, I like that option because I'm often not at the facility during the test. And then I can also look at this stuff because I have access to DesignSafe and be part of that decision-making process. And then, yeah, another question from Faisal Rehman. Is it possible to get data in Python from LabVIEW or from the DAC directly? And what modules are used, or some resources for this purpose? So I think you were reading the binary files as they come out of your data acquisition system, right?
Yes. Yes. So I believe there are ways that you can interface Python directly with LabVIEW. How I was extracting the data from LabVIEW was just getting binary files out from the LabVIEW program, and then using that and reading that in with my Python script. So it wasn't necessarily a direct integration. There was kind of a cold stop there with the files being saved in a binary form, and then me pulling those and uploading those and doing my data analysis techniques on them.
And then let's see, we also have a few comments coming in through the chat, so I can read those too from Michael Scott. Great job, Trevor. Python and Jupyter notebooks can have some pretty significant cold start times, loading packages, etc. Have you had any issues with cold starts in real time?
I have not. I haven't had to address that issue specifically. I do know it's there, and I think this is where I think moving stuff from maybe perhaps a local system to the design safe framework can kind of maybe minimize some of those cold start times, because those are always those scripts are kind of running in the background. So I haven't had to address that specifically, but I think that kind of goes back to I'm just right at that tipping point of the analysis taking too long to run on a local machine. Yeah.
One thing that I've done, I don't want to kind of take over, but I'll just mention that Python is not the most efficient language. A lot of things run pretty slow because it's pretty far abstracted, but there are options to build your Python code in C or something that's a little more direct, that's more efficient. And so there's something called Python, and I've built codes that run about 150 times faster just by declaring a few variables and things like that. So if anyone's interested, you could feel free to reach out to me about that too. And then I had a question too about real time. I've been talking to Gilberto Mosqueda, who's also involved with Design Safe, and he does hybrid simulation so that there's a finite element model that is informing the control system to change things. And so that's when he talks about real time, I think he means something different than you, right? You're talking about real time being that you do the event, shake the model, and then you're looking at data in real time during the experiment as the centrifuge is spinning. But can you clarify, what you mean exactly by real time?
Yeah, so I guess real time is the times. When I say real time, I'm thinking of the time scales that I usually work in for experimental processing. So that is, when I say real time, I mean within about 5 to 10 minutes of the event. So getting the data off the system, uploading it to locally, running my Python scripts, doing my data analysis, and then generating the data that we then use in the decision trees.
Right.
One of the challenges, I think, of doing hybrid simulations real time on the centrifuge is, again, our motions are, Scott, as you know, probably the motions are 0.2 of a second. So we're like that. And so to try to do a numerical simulation where we're kind of doing a closed loop control or some kind of loop control on it is a challenge. I don't know if we can address it at this current time. I think in the future we may be able to do that, but it's a little far out there right now.
Yeah. There's also a great question from Laura Luna. Do you write the code collaboratively with others in the team? And if so, do you use Git or something like that for version control, or do you write all the code yourself?
Yeah. I would say we typically write as a team, and maybe not the direct one person works on one aspect and one person types a little bit more, but when I say a team is you share code that people have developed in the past and kind of integrate that into what you're doing, or you look at the analysis that they have run and you integrate that into your code processing framework. So it may not be like a Google Doc or a Git document where everyone's just going line by line, but we do share code. I think the last code set that I developed for this latest centrifuge experiment was I worked with about 3 to 4 people here at Davis that have done it before and used some of their data for my validation procedures and kind of integrating what they had done in my same framework as well. So it is I think it's a highly collaborative process because it's kind of an unknown to a lot of people. What do we want to look at? And then just being able to work with kind of big data sets is a task in its own that's sometimes a challenge. So.
And kind of to follow up on Laura's question, have you thought of publishing some of your code bits or your scripts that are used frequently, like maybe filtering acceleration data or computing acceleration response spectra using something like the Python package index PyPI that would allow other users to pip install your functions and run them?
I have. It's just the barrier of trying to get that all wrapped up and kind of into a state where it'd be acceptable for use in the community. I think my sharing now is all internally, but I would have to kind of go through and clean stuff up a little bit. But that is definitely out there and something I'd like to do, because these codes are no small feat to write. I mean, there is a lot of knowledge that goes into them and a lot of time. So it would benefit people, so they don't have to redo that. I think that's a real benefit of not having to go back through and redo what we already know. So it's out there. I haven't done it yet.
I think if you're like me, writing code is fun, writing documentation is not. So that tends to be the problem with releasing it. So Charlie, should we call it there?
I'm not sure if Fazal's question was actually answered or not. Was that his other question was what modules are being used or resources for this purpose? He wants to know the purpose being, how do you bring data into Python from LabVIEW or DAC? Yeah,
so kind of how it's set up at the Centrifuge facility right now, and this will be unique to every place, is Dan has a robust data collection system where you sample your sensors during shaking, it saves data, and then LabVIEW actually exports a binary file. And within that binary file, there's some text at the top that says what sensors were sampled and kind of what sensor parameters you had in there, sensitivities, serial numbers, and then you have the raw data. I then take that data into Python, and I created a binary to ASCII script that I created, and this was specific for the Centrifuge and how Dan has laid out his data files. There's specific things in specific locations, such as sampling rate, the number of sensors, and then where the data occurs. So I developed kind of a binary file that would take, or excuse me, a conversion file that would take that binary and then make it and turn it into some kind of ASCII text.
Okay. Hope that answers your question, Fazal. All right, thank you so much. All right, let me share back. Oh, come on. All right. And share. All right, so thank you so much everyone for attending. All of our training are archived in the Design Safe Training Archive, which you can get to by going to designsafe-ci.org to the Learning Center under Training. All of our videos are also on our YouTube channel. So if you just go to YouTube and do a search on Design Safe, you'll find our Design Safe YouTube channel as well, where all of our videos are documented. All of the material and the slides are also going to be linked off of our Learning Center page. So I want to, again, thank everyone for joining us today. We do appreciate your feedback once again. So if you missed the survey link, here's the survey link again. You also should have received that in your email earlier today or earlier this.
Hey, Charlie, I think you may be sharing the wrong screen. We're not seeing.
Oh, I'm sorry. That's all right. Let's try that again. My bad. Desktop 2 and share. All right.
There you go.
Better.
Perfect.
Sorry about that. I'm kind of curious what I was sharing. All right. Once again, here's a link to our training archive, https://designsafeci.org/learning center/training. You can get that too also from the Wayne site under Learning Center and Education and Training. That's where all of our videos are at, and links to all of the material that you saw. As soon as this video gets curated, will be posted to the Design Safe site. Of course, special thanks to Trevor Carey for joining us today, and thank you very much for showing us your process on making the decision trees. We really appreciate that. It's great knowledge. And also, your feedback is very important to us, everyone. If you missed the link earlier, here's the link again. Please go take some time out, fill out the survey. This will help us make and put together better webinars that fit your science. Once again, thanks a lot, everyone, for joining us this afternoon. We hope everyone stays safe, and we'll see you next time. Thank you.
Thank you.